Hello, good afternoon. As she said, I'm Guillermo Nery, and I'm filling in for Abel Mendez, presenting the results from the Planetary Habitability Lab's second Earth-like Worlds workshop, where we studied habitability metrics for astrobiology. If you like, you can follow us on Twitter. Okay, so what is habitability and how is it measured? If we look at the map, you can see that we have global terrestrial habitability for primary producers as indicated by the net primary productivity. And if you look at the equator, you can see that the most productive areas or the most habitable areas are where we have forests. Okay, so what is habitability? Habitability is the suitability of an environment for life. It's formally known as habitat suitability in biology, specifically in ecology. And habitability is usually quantified with indices that vary in value from 0, not habitable, to 1, which is habitable. These indices are an indication of the presence or abundance of some of the requirements of life. A common misconception is that these indices need to consider all environmental factors to evaluate the habitability. Habitability is always evaluated by parts to understand the individual contribution of one or more environmental factors, and a library of indices is usually constructed to characterize an environment. So, we're presenting a general mass energy habitability model. Current habitability models, for example, the habitat suitability model, gives us a habitability index that's proportional to the carrying capacity of an environment. And so we get a numerical index that measures the capacity of a habitat to support a particular species or community. Our general mass energy habitability model gives us a habitability index that's proportional to the mass times energy that's available in a given environment. So we get a numerical index that measures the mass energy capacity of a habitat to support life. And how we get that index? Well, we have to define a volume of interest and an amount of time we're going to watch that volume. We measure the amount of energy going in, and we measure the amount of gases, of liquids, and solids in that environment, in that volume of interest. And then we go ahead and make the calculation for the mass energy habitability index. And here we have an example. Here we can see mass multiplied by energy and compared to a reference. And this is how we get the mass part. You can see it's a geometric mean of all of these masses. By the way, these masses do not include we don't include biomass. It's just the environment. So we're using volumes and densities and the geometric mean, and we're getting a normalized mass because we're comparing it to these reference values. And this part's the energy, and we can see that for this particular case, we're using the temperature. So we're talking about thermal energy. And let's use that. And so we have the mass energy habitability index for some terrestrial environments. Now we're considering, sorry. Let's go again. Okay, so we're considering 4 basic habitability elements. We're considering the amount of gas represented by air, the amount of liquid represented by water, the amount of solid represented by earth, and the amount of energy represented by fire. So this is a little bit poetic, but it's also somewhat accurate. Okay, so our reference is the rainforest of El Yunque in Puerto Rico. And since it's our reference, it gets a mass energy habitability of exactly 1. Now we're going to compare other biomes to that particular one. And if we look at the ocean surface, tropical, we get a habitability value of 0.286. Why so low? Well, while in the rainforest we have lots of air, lots of water, lots of solids, and lots of energy, The ocean surface has lots of air, lots of water, lots of energy, but not so much in solids. And that solid you have there, it's not that there aren't any solids in there, but it's that it's a limiting factor. There's little of that, and so it drives the value down. If we now go to the ocean depths, you can see that the value is even lower. Well, here, what do we have? We have lots of water, lots of solids, but very little gases and very little energy. So you get a lower value. And if you go all the way to the clouds, you get almost zero. Why? Lots of air, lots of energy, but comparatively small amounts of water and solids. So those limiting factors are very important in bringing the values down. But if you look at this, more or less, it seems reasonable. More or less what one would expect from these for this index and for what you would have for habitability, comparing them. But now let's see if this is actually valid. So here we have validation using terrestrial biomes. What we did here is we compared the mass energy habitability. It was calculated for each of those biomes. And it was compared with the productivity, the NPP, for 12 terrestrial biomes. And you can see the data points, okay? And they make a nice little line there. So this relation can now be used to predict the expected magnitude of biosignatures. For example, higher global NPP means more photosynthesis and thus more atmospheric oxygen produced. Okay, so now we validated this. Let's try and apply it to planets. Now this is a model for an upper limit for planetary surface habitability. And we assume that this is going to be for planets with a similar land, ocean, and atmosphere composition to Earth. And here we have the energy part, that's this and a part of this, where we're using the stellar flux and the surface of the planet. And then for the amounts of solids and liquids and so on, we're considering a thin surface layer, okay? And we need, well, the ocean fraction. And we're assuming, if we don't know how that planet is or where it is in time, how it was at a certain point, we're going to consider in this case that the atmospheres are the same, so that'll cancel in this equation. And we only need the ocean fraction and to get the amount of ocean and the amount of land. Okay, so this would be our mass energy habitability index for planets. Our comparison is with Earth, okay? So let's apply that. Applying that to early Mars with an ocean. So Earth is our point of reference, so that Earth then has a mass energy habitability of 1 with a global MPP of 105 gigatons of carbon per year. Now, comparing that to early Mars with an ocean, the mass energy habitability of early Mars would be 0.02, and that would correspond to a global MPP of 2.4 gigatons of carbon per year. So that early Mars with an ocean was at least 40 times less habitable than Earth today. Okay, so in conclusion, habitability metrics allow us to identify and prioritize targets of interest, simplify our understanding of habitable environments, and compare results from simulations. For example, some people are creating climate models for exoplanets. You could use that for that. The mass energy habitability metric was constructed to characterize the potential habitability of environments based on the maximum quantity of mass and energy available for life. A different metric could also be constructed to evaluate the quality of the environment. Our mass energy habitability was validated using terrestrial biomes. And we see that the general trend is that the suitability of planets to sustain a larger biosphere increases with the fourth power of their radius, given that all other conditions are similar to Earth. Therefore, a biosphere on planets slightly larger than the Earth, for example, super-Earths, might be more susceptible to atmospheric chemical disequilibrium, in other words, biosignatures. And that would conclude the talk. So any questions?
All right, if you're able to get to the microphone to ask your question, please do so. Otherwise, just raise your hand and we'll try to spot you.
Thank you for that talk. So your model is based on that it has exactly the same atmosphere, land, ocean, and so on as the Earth in proportion.
No, it doesn't have to have the same proportions. It's just similar. So that you have land, you have a rocky planet, it has some amount of water, and it has some atmosphere. But we would expect, we would want the composition to be somewhat similar.
So what would the index be for Venus?
We haven't made that calculation, but given that it has very little water to start with at that point, but
Right.
well, that would basically give it a very, very low value.
Oh, well, that's with our knowledge that it has no water, but in the context of an exoplanet, you're just using the radius.
Okay. In the context of an exoplanet, we would basically need to model that exoplanet and the conditions for that exoplanet. We wouldn't be able to evaluate it until we get more information, and then we could apply that. But basically, in terms of exoplanets,
more information for Venus means measuring the surface temperature, really.
Yes, measuring the surface temperature. If you can get, at this point, we can already start to identify materials in the atmospheres of exoplanets, and probably a little bit later on, a few years later on, we'll be able to measure other aspects of the exoplanets. So that's when we would be able to get actual values that are, more indicative of an actual exoplanet. But in the meantime, we could still model exoplanets, and this is still useful for that purpose, to be able to compare exoplanets based on the models.
Okay, thanks.
Welcome.
Hi, this is Renee Heller. My question is the biomass production rate, if I remember correctly, goes with, as you say, the radius of the planet to the fourth.
To the fourth,
so the
yes.
First question would be, where does the number 4 come from? And second, there is no cap, obviously, so a Jupiter would have the largest biomass.
Okay,
right?
so there are two things. First of all, we're working with Earth-like planets. So Jupiter is not Earth-like, and okay, so what we would do is, we would compare Earth, super Earths, smaller planets that are similar, but there's a limit to where the super Earths lie, but I don't quite remember where it was. There's a certain particular value where you start getting gas giants.
Where does number 4 come from?
Oh yeah, the number 4. Okay, so you look at this over here. Part of this comes from the surface of the planet, and part of this comes from the volume. And this is because this happens where we have the stellar flux times the area for the energy, and then you would have another R from the volume considerations. So it's a little bit of volume and a little bit of surface, and that's where you get the R to the 4th power here.
Okay, we can take one more question if it's a quick one.
So the claim would be that the habitability, if the value is high, the planet is more likely to be habitable than if the value is low. That is the ultimate aim.
Could you repeat that again?
So a high value of the index should mean more likely to be habitable. It's a quantitative scale.
Yes.
But surely with the number of parameters you're missing out, magnetic fields, presence of water, rock type, actually there is no quantitative scaling between the value of that indice and the chance of the planet really being habitable in reality.
Okay. At this point, what we're doing is we're basically putting an upper limit to the habitability, and later on we can develop this model or other indices so that we can take those things into consideration, how those factors would affect how much of the solid, liquid, and gas is really available for life.
So I think I would argue that such metrics are quite good for sample selection to try and look at the planets for more information. But I think to say it is quantitatively proportional to habitability is just wrong.
Sorry, we're just going to have to cut the questions there. Let's give Guillermo another round of applause.
Okay, thank you.